Hi, my name is Eric Culverson. I am the authorized training provider for AMD for the Southwest region, and I'd like to welcome you to an introductory training that leads into the full classroom training. We're going to walk through a particular lab exercise with regard to the Versal platform, and it's called the Versal System Design Flow. And we're using this as a vehicle to understand some basic concepts about Versal, the integration, the various subsections, and the design flow. This particular lab teaches a really important concept when it comes to personal design, and that's that it's going to be a divide and conquer approach. It's going to be a top-down analysis, excuse me, but a systems up development. And that means that we need to build individual components, test and verify each of those components. Then at some stage, we start to pull those together into a system level design. And then we verify at that stage. A whole nother level of effort would then be optimization, looking at our data flow, looking at our latencies, looking at everything that it takes to move data from one section of the device to another. So this exercise that we're going to walk through here, it's going to take roughly about 2 hours to complete everything because we're going to do a little bit of overview. We're going to do just a little bit of lecture, and those concepts are going to be reinforced during class. The same things we're talking about here, we're going to discuss them in a lot more detail during the training. So let's start there. Let's bring up a slide deck that deals with the overall architecture. And we're going to look at this in two stages. One being the original Versal Gen 1 product, and then the second being Versal Gen 2. And we take it in that order because Versal Gen 2 mostly looks at enhancements and features and other options that have been made available as part of the overall Versal platform. And this is now a new subfamily that you can take advantage of. But with regard to the basic design flow, most things in Versal Gen 2 are based on Versal Gen 1. So that architecture, that design methodology, that's where we start. That's what gives us the fundamental basis of understanding so that we can then leverage the Versal Gen 2 resources. So let's go to this particular slide. And if you've looked at any Versal training or Versal literature, this is typically what you see. This is the picture that's shown. It's not quite anatomically correct in that although it highlights the various features and subsections, they're not quite in the right order here in terms of their location. But we'll discuss it as we go forward. So the three primary subsections to any Versal platform will be the processing subsystem, which you see here on the left-hand side, the programmable logic, and then the adaptable engines, which include the AI engines as well as the DSP functionality. So let me bring up my cursor. So what exactly are these resources? You've got the processing subsystem, which consists of the ARM-based A72 processors, and you have two of these in the original Versal Gen 1 product, and you have two real-time processors. So that means you have this set of different resources that can be used based on your application, based on the level of computation you need, based on whether you need determinism. So you have this heterogeneous compute environment. You also have this platform management controller, which you see on the left-hand side is more or less part of the processing system and is tightly coupled with the processing subsystem, but it is independent. In fact, the platform management controller is actually responsible for the larger device configuration. It actually sets up the processors. It is responsible for the initial boot and configuration of the overall platform. And there's a lot of detail there, depending on whether or not we're doing a secure or non-secure boot. Once that boot process is completed, then the platform management controller continues to manage throughout the life cycle of the part. So it's doing everything from debug to tamper detection and response. You also have, in some devices, this accelerator RAM. Now, not every device has this. In fact, if you look at the overall family, not many devices have it. But to the extent that it's there, this is a 4 megabyte chunk of just large memory that you can use as global RAM. And we need global RAM in the case of hardware acceleration, which means that we are offloading some tasks from the processor, and we implement this in the form of a kernel. And that kernel can be in the programmable logic, or it might be in the AI engines. But we need a way for the processor to prefetch the data that's going to actually be processed and move that to a memory space that's accessible to both the processor as well as the kernel. So that's what the accelerator RAM would do in that situation. So for devices that don't have the accelerator RAM, then you're simply going to use the block RAM or the ultra RAM for that same functionality. Then you have the programmable logic, which in the Versal devices is upgraded from the previous families. The layout of the CLBs is different. They tend to be larger. A lot of the internal routing compensates for what used to be external routing and the muxing structure, which reduces internal routing congestion, making it more efficient. And 1/2 of the programmable logic can be configured as RAM or as like a shift register lookup table. So you once again have that flexibility of either digital logic or distributed RAM or the SRL resources. The AI engines, and this is part of what I mean when it says not quite anatomically correct here. The AI engines always exist to the north of the programmable logic fabric. And that's an important consideration because part of your system architecture considerations is how do you move data into and from the AI engines. So that requires typically moving data from the programmable logic in a north-south direction to the AI engines, which would physically be situated here. You're processing data using the vectorized SIMD operations for speed and performance, and then you're moving that data back to the programmable logic. There's also an option, of course, to read from memory and to write from memory. But in the case of a real-time application, so like a filter processing, you most likely are going to be reading data directly from the programmable logic into the AI engine. And that's actually what we're going to see in this lab exercise. That's the way the data path is constructed. The DSP engines are once again shown here as separate, but that's just to highlight the fact that they exist. They don't really exist separately. They are part of the programmable logic, similar to what you had in previous families with the DSP 48. The Versal devices have the DSP 58. So not only is it larger with a wider multiplier, but there are new operational modes and there's some new capabilities and features there. So everything about Versal represents either completely new functionality, higher speed processors, and even the things that are technically the same as before have also been updated or in some way enhanced. And then you have the NOC. And the NOC is a really key part of the overall Versal methodology, layout, communication scheme. The NOC is basically an AXI connector. So any AXI master anywhere on the device can talk to any slave through the NOC. Now, that's not the only way for AXI masters and slaves to talk, because within the programmable logic, you could continue to use the standard AXI interconnect IP, or if you have a single master talking to a single slave, then of course you don't need any connection whatsoever. But this gives us a high-speed data path for moving information from any portion of the device to any other portion of the device. So that flexibility is there to make every portion, although they operate independently, with regard to sharing data, that can be done seamlessly and efficiently using the NOC. And this will be a big part of our training, understanding how to assign data paths to the NOC, designate a particular quality of service, and then be able to simulate that, verify the functionality. You then have a lot of interfaces to the device, including a hardened PCIe interface. So this is important because in the past, if we were doing PCIe, then it would have been in the programmable logic. And you still have that option. But here's the advantage. By having a dedicated hardened block, if this device is acting as a PCIe endpoint, then this is a dedicated resource that's able to boot up immediately. So it can meet the 100 millisecond enumeration requirement for the overall PCIe interface. So that means we're not having to do tandem configuration. And that's a design scheme where we load enough data into the programmable logic to get the PCIe interface up and going. Then we come back and separately load the remainder of the bit file. You have the DDR, low power DDR controllers. These are actually tied directly to the NOC. Now, are these the only resources you have? No. You could build DDR controllers in the fabric and just tie that directly to high-speed I/O. But these dedicated controllers are going to give you even better performance, lower power, and more flexibility. But again, they are tied directly to the NOC. So each controller for the DDR4 has 4 slave inputs. So that means I could have 4 masters from anywhere, from the programmable logic, from the AI engines, from the processing subsystem, from the platform management controller, and they can all talk to memory through this resource. The number of these that you have, the total number, depends on the size of the device. So for instance, in the 1902 device, which is what the VCK190 board is based on, you have 4 DDR4 controllers and 4 vertical channels of the NOC, which ties directly to the NOC, to the DDR controller. Some devices will also support high bandwidth memory. So this means you're going to have large memory that's built into the package. It's literally packaged along with the die, and then using a silicon interposer, they connect the memory directly to the die. So you have extremely wide, high bandwidth memory interfaces. So for applications that tend to be memory bound, then this is a workable solution for that. You're going to have a range of gigabit transceivers. On the low end, 32 gigabit is now really just the price of entry. The higher ranges include 58 up to 128 gigabit per second lanes. Now, which of these you have depends on which device. So in the premium devices, you're going to have the 128 gigabit capability. In all devices, you're going to have at least the 32 gigabit capability and some 58 gigabit capability. You have also the 100 gigabit Ethernet core. And this is actually a multi-rate core. And we're going to be talking about that a lot in our class on day 3. This can be configured as a single 100 gigabit Ethernet lane or 2 50 gig E lanes, 4 separate 25 or 10, 1 separate 40. So there's a lot of flexibility to configure this to support different protocols and different applications, and you can change it. You can change that either statically based on your application or dynamically as your needs change in the operational mode. You also have other cores. So interlocking cores, a variety of different high-speed interfaces. Standard protocols are supported. You've got a dedicated video decoder. This is going to give you the ability to just encode, decode video, and this is based on the ARM Mali. You've got direct RF. So the Versal RF devices have onboard ADCs and DACs, so we can do direct sampling, and we can take that data directly into the parts, so we now have a single chip solution. This is similar to the Sync RF MPSoC families, or RFSoC, but we have the benefit now of the Versal fabric rather than the MPSoC fabric, which was based on the UltraScale Plus architecture. And then you have other interfaces. You've got, of course, GPIO, that low voltage differential signaling, and you also have dedicated MIPI interfaces. So this is the original Versal devices. On the next slide, we're going to be looking at Gen 2. So as we said, the Versal Gen 2 is an enhancement. It basically takes Gen 1 and adds a lot of great features. And it begins with the processing subsystem. So rather than having two A72 processors and two R5 processors, you now have up to 8 A78 processors. So even higher computational rates, as well as a lot more processors. So this is up to 200K data MIPS. And these can be clustered together, and they can run in independent mode or lockstep. So architecturally, they are clustered into 4 groups. And within that group, the processors can run independently or in a lockstep mode. And that's an immediate difference from what you had in the Gen 1 product, where the APUs could not be clustered. You could run them together using symmetric multiprocessing, but you could not run them in a lockstep mode. The real-time processors, you have up to 10 R52 cores, once again, able to be run independently or within the 5 clusters. Those can also run in a lockstep mode. And in both cases, running them in lockstep gets you all the way up to ASIL level D. So we'll talk about that in more detail throughout the training. There are some enhancements to the AI engines, mostly support for advanced data types. So if you're doing machine learning applications, then these are extremely effective for being able to do kind of a reduced accuracy floating point data types. So these are block data types, block floating point data types, where you have a common exponent and then different mantises, either 6-bit or 9-bit. That ability to run the processors in lockstep, again, gets us up to ASIL level D on both the APUs and also the RPUs. And a big enhancement to this particular family is something called the ASU. This is the Application Security Unit, which is a triple redundant MicroBlaze-V controller that does cryptographic services for the larger device. So we can have applications that are running on the processors or possibly on other MicroBlaze processors within the programmable logic, and they can all leverage the ASU for their cryptographic operations. So this is encoding, decoding, hashing, symmetric, asymmetric, key management, utilization of the POF, the physically unclonable function, to do key encoding. So this is a completely self-contained, flexible, able to support other processor operational unit. You've got hard video processing, which means that you've got dedicated blocks. And the importance of dedicated blocks is always that they give us speed, they are going to be low power, and they're going to be configurable. So we're not using programmable logic fabric, but we have image signal processors. So this is going to act as a front end So let's say you're doing a machine learning application that involves image classification and segmentation. So you're capturing data, and typically you need to do some pre-processing to feed that data into the machine learning model. So here you've got hardened resources that allow you to do that, along with hardened video codec units. So supporting 264, 265 encode, decode standards, and pretty much everything that you need to have a fully self-contained video processing channel on the device. High-speed connectivity, PCI Gen 5, 10 gigabit Ethernet support, USB 3.2, DisplayPort 1.4. You can also boot the device using universal flash. High-speed memory, the DDR5. Actually, there's still support for DDR4. You can configure the DDR memory controllers to be DDR5 or DDR4 or low power DDR5. And one of the new features is this selectable inline encryption decryption. That gives you the ability to take the memory that you're writing to, divide it up into 16 different segments, and treat those segments as individually secure. So you can encrypt and decrypt data as you write and read to the memory. And again, this is built into the memory controller itself. You also have an integrated GPU, which is based on the Mali G78AE, the AE meaning automotive certification here. So there is redundancy. You've got 4 shader cores organized into 2 sets of 2. So they can be independently operated, either for redundancy and backup or to just support different displays. So you've got 2 or 3D GUI rendering here at like 4K by 60 resolution. And high performance IO, 1.2 volt LVDS up to 1.6 gigabit per second. And that's not using transceivers, that's just ordinary IO, 10 gigabit per second, MIPI, Control PHY, and Data PHY. So a ton of enhancements to the Versal Gen 1. And one of the common themes that you see with Versal Gen 2 is a lot more compute capability, a ton of additional security and safety features and enhancements, including the ASU, including the ability to do inline encryption decryption through the memory controller, as well as all of the secure boot features that are already part of the platform management controller. So once again, all these things we'll talk about in great detail throughout the training. So that's our overview. Now let's get back to the lab exercise. So we're going to get out of this and we're going to run the tools as we do in our training classes using this virtual machine. And we use a virtual machine because, like most people, I have a Windows host, and that's what I typically use for my own computer, and that's what most of the trainers use. But to do Versal development, design, testing, and methodology, you need to be using the Linux version of the Vitis tools. Having the Linux version of Vivado would also be good, but it's a necessity for Vitis. So having a virtual machine allows us to run the Linux versions of the tool, even though this is a Windows host. So that's what you're seeing on the desktop. This is a virtual machine that is configured by the Customer Education Group, and this is what we use for our training. So we're going to run this specific lab exercise, and I'm going to set up my screen so that I have the software to the left and the lab instructions to the right. I also want to take this opportunity to talk a little bit about how the labs are documented, because throughout the class, you're going to be doing various exercises, and you're going to be walking through and seeing pretty much the same structure, even though each lab exercise will, of course, focus on a different aspect of the design methodology. So you have a title for the particular lab. In this case, it's the Versal System Design Flow. You have an abstract that gives you a really, really broad overview and an estimated time for this particular exercise. There is some instructions for people that may be using the CloudShare resources. Then we get down to the specific objectives. So for this exercise, this is to integrate the I/O capabilities in what we call the graph. And the graph is how we represent AI engine data flow. We're also going to compile functions into the programmable logic, and that's going to be done using the HLS functionality. You can also, of course, use VHDL Verilog to create functionality for the PL, but there's some distinct advantages to using HLS, and I'll talk about that a little bit here, and we'll discuss it in more detail throughout the training. We're going to compile those graphs. Then we need to create a configuration file that describes the system connections. Ultimately, in this exercise, we're going to take the lower level components that we've created, and then we need to represent those in a larger system. So how do you do that? What are the exact steps? How do you combine those low level components? We're going to walk through that. We're going to show exactly how that process looks in terms of the Vitis design flow. Then create a fixed platform using the base hardware that includes all the submodules that we've created up to that point, compile the host code, and then ultimately run simulation, or what we would more specifically call hardware emulation, at the system level. And the reason we chose this particular exercise is that it demonstrates some of the most important and fundamental concepts with doing a versal design. So even if you're not using the AI engines, as this particular lab shows, the design steps that we're going to go through, the process of building individual components and linking them together in a system level, that is the same. The process of testing each one of those low level components before we do the system level assembly, that's the same. That's part of the design methodology and part of the thought process that we need to adhere to when we do a versal design. So the next part of the lab gives us an introduction, and typically what's here will be a little bit of a repeat from the lecture and presentation. So they remind us of those important concepts that this particular lab is intended to demonstrate for us. In this particular case, once again, we're combining different elements. Now, this particular diagram talks about the flow and the order in which things are done, but let's come back to this. Let's skip down and look at this picture. This is what we're actually creating. So I want to just move this over a little bit so I can make that a little bit larger. So if you look at this particular diagram, we've got functional blocks in the AI engine, which is indicated here in the green. We've got functional blocks in the programmable logic, which is indicated in blue. And then we've got code that's running on the processors, which is indicated here in yellow. So for a system level design, we are tying all these components and all these individual operational blocks together. And we know from looking at the original picture that these are individual subsections. So how do they communicate? How do we move data from one section to the other? Part of that can be seen here. Notice the direction of the arrows, where we are moving data from the programmable logic into the AI engines using this north-south connectivity. So remember that the AI engines are always physically to the north of the programmable logic. So we actually use channels, actually streaming channels that run north-south between those two resources. The data flows from one kernel to the next kernel to the next kernel, and then the result of that feeds back into the programmable logic. And on this end, we are reading from memory. So this means that we need a memory mapped interface that's capable of then writing to a streaming interface. So the kernels and the programmable logic are the memory map to stream and the stream to memory map based on which direction we're moving in. And again, all of this is controlled in a broader sense by the processor. So a total of 5 different kernels. Now, we're not going to get into a lot of details on the kernels in the AI engine, except to say that the first one is basically a half-band filter. The second one, which is actually a polar clip, is going to determine the magnitude of a complex output, and then the classifier determines which quadrant that output would go into, basically anywhere from 1 up to 4. The output results are once again piped to back into the programmable logic through this streaming interface. So ultimately, we're going to create a system project. Now we can only do that after we've created the lower level components, and those lower level components are going to be kernels running in the AI engine, kernels in the programmable logic, the application code running on the processor, and then we need to explicitly tell the tool how elements in the AI engine connect to elements in the programmable logic. And that is something called a hardware link file. And this is something that we edit by hand to explicitly show the connectivity. And all this together then forms the system project. So the design flow, once again, is a top-down analysis, a bottoms-up synthesis and compilation, where we're creating individual subblocks. We are verifying each subblock. So as you develop these low-level components, you also need to develop a test bench. You need to have a way of verifying the functionality of each module before you make it part of the larger system. Like with any design where you are looking at the integration of different blocks, those different blocks should, of course, be independently verified before we bring them into the top level. So as part of the Versal design methodology, be prepared to create test benches along the way. And we'll give you a really quick example of how that might look in the Vitis platform. So now we can go back to this picture. And this shows us, using numbers, the individual steps that we're going to go through here. Everything begins with the hardware definition. So in any Versal design, like MPSLC design or any other platform design, we always have to define what the actual hardware is. And in this case, it's going to be based on the VCK 190 platform. So that is a 1902 device, which is the largest device in the original Versal family. We then start compiling the source files for the individual kernels. And we've got kernels in the programmable logic, and we've got kernels that are running in the AI engine. Notice here in the green that the AI engine compiler is being run. So that's a dedicated compiler. If you have logic in the AI engine, then anytime you do a build, that's using the AI engine compiler. Now that is already built into Vitis. It doesn't show up as a separate tool, but that is the necessary compiler for doing anything related to the AI engines. For the other modules, we're actually implementing these as CPP files, basically C++ files. And the memory map to stream and the stream to memory map are both going to go through high-level synthesis. And that's going to actually create the hardware functionality that will go into the programmable logic. Then those need to be connected together. So that's what happens with the system linker. And that's where this configuration file comes in, which we hand edit to explicitly show the connectivity between these resources. And from there, we can do now system level simulation. We can take this to the next stage. Notice that this actually updates the .xsa. So this is what we would call a extensible platform. We start off with one version of the .xsa, but because we're adding additional logic and functionality in Fidus, we effectively update the .xsa. And this now gives us the ability to take the complete system and package this along with the host code that's running on the processor. And now we can run hardware emulation. And the key thing about this hardware emulation is that these three colors represent that three different processors are being run. So you've got logic in the programmable logic, you've got code running on the processor, you've got functional blocks in the AI engine. Each one of those actually requires a different simulator. So something that's built into the Versal design flow is that Fidus is capable of actually running all three of those simulation tools in one integrated fashion so that you can literally see data movement from the programmable logic over an AXI interface into the processing elements of the AI engine. And all this happens under the control, once again, of the code that's running on the ASU. So you've got three different simulators. Quick emulator for the code that's being executed on the processing subsystem. The Vivado simulator for the functional blocks within the programmable logic. And then the AI engine simulator for blocks that are specific to the AI engine resources. So we're going to see all of this as we go throughout the lab. Each lab will also have this little boilerplate documentation about understanding the lab environment. And this is really just looking at the specific interface and how the labs are organized within this virtual machine. That is only relative to operating during the class time or running labs in this specific environment. If you are using the lab source files and the documentation in your environment, then you can set the files in the way you want, and you can launch the tools from wherever you want. So none of this would matter. Then we get down to the actual flow of the lab. And as you can see in this case, we've got quite a few steps. We have up to 10 different steps, starting with just launching the Fidus tools. So that's where we're going to begin. We're actually going to start with launching Fidus. And so we begin with launching the Fidus tools. From the menu, if you notice the instructions, we actually have the option of starting up the tools from the terminal window. And all we need to do, according to step 1-1-2, is point to the proper configuration file. And that would be located based on your particular installation, but it's just a lot easier to simply click on the icon. So when we start up the Fidus tools, we always need to specify the workspace. On the workspace is where all the files that we're going to create, all the compilation is going to take place in that environment. That workspace also has a ton of metadata associated with each and every file. And for that reason, you cannot simply move files and folders into this particular directory. You need to use the explicit commands that are in the Fidus menus for either importing files or exporting files. But again, we do not just go into File Explorer or Window Explorer and move files into this location. That metadata has to be maintained, and that has to be intact for each and every file source. So we started up the tool. Now we're going to specify the workplace. And the workplace for us is based on the particular lab folder. And for the purpose of what we're doing, this is under Home, Training. The folder for the lab is called System Flow, and then Lab. And this is actually an empty folder at the moment, which brings up another important point. when you are setting up a Fidus workspace, you have to point to an existing location. Now, there doesn't have to be anything in that location, and it's perfectly okay if it's empty to begin with, and then you start importing your source files, you start doing compilation and other operations. But that initial workspace that you point to has to be an existing location. So if you look on the screen right now, you see that the workspace has been defined, but again, there's nothing here. So everything's completely empty. So the menu prompts us to create components. Those components could be HLS components, AI engine components, application components, which means that's the source code that's going to run on the processor, a platform component, or a static library component. Following the lab exercise, we're going to begin by creating an AI engine component. So we can simply click here, or we can go to the menu, say File, File, New Component, AI Engine. And according to the lab instructions 2-1-3, we are labeling this as Versal CoSim _AIE. The component location will be our current work folder. We click on Next, and now we're going to pull in sources for this. And we've got two different sources that we're going to bring in. There's the actual source files for the kernels that are in the AI engine, and there's also data files. And those data files represent our input stimulus for our test bench, as well as an expected set of outputs. So when we add sources, we can add individual files or folders. So I'm going to click on Add Folders, and I'm going to browse to the location where those folders exist for this particular exercise, which is going to be under Home, Training, back to the same project folder, and now under Support, there's an AIE folder. So I'm going to open that. And I'm going to do the same thing again to grab the data folder. So I will click here once again and just go down the same path, Training, System Flow, Support, and grab the data folder. So now I've imported two different folders, each one with a respective set of files, and the tool actually looks at that source file and analyzes what the top level should be. Now I have the ability to change that here if for some reason it doesn't determine the right file. But this is the correct file. The graph.cpp is the top level test bench file. Everything else gets referenced underneath that. We make sure that it copies the sources to component, and then click on Next. And now we need to specify the platform. And the platform that we're going to be using throughout is the VCK190. So we select that. If I had started this in Vivado and did my hardware definition and exported the .xsa file, then at this stage, I would say hardware design, and I would browse to that particular .xsa file. So again, for the purpose of this lab, we're choosing the platform from this list of available platforms, which, by the way, you would download this directly from the AMD website. And we're selecting the VCK190, click on Next. We get to the summary screen, verify all the selections and choices we've made up to this point, then click Finish. So now the first component for this design has now been defined. So this is the label that I gave it, Versal CoSim AIE, and the type of component is AI engine. If I expand this, we can see that under sources are the two folders that I pulled in, the AI engine folder and the data folder. Under the AI engine folder is the code for the graph, the code for the individual kernels, along with an include file, which has a function signature. So we're not going to go into great detail on the coding for the AI engine at this point, but in this particular project, we are combining an AI engine with other modules to create the overall system. In the data folder, let me collapse that, expand this. There are two folders here, one called input and the other one called golden.txt. The input is actually my stimulus. So when I run the test bench, it's going to read from this particular file called input.txt. And once the simulation is done, it's going to create a file called output. Now, those names are not just random. Input is the name that was given to this particular file, and output is the name that's designated by the user for the specific output from the simulation. I'm going to be able to compare the results of output to this golden.txt. So that means that at some point, the lab was run earlier and the outputs were captured. And now I can use those for the sake of comparison. Keep in mind that as part of this design flow, when you are creating these lower level components, you're also creating a way to test and verify each one. So that means having a defined set of stimulus and hopefully having something that you can compare to the outputs. All right, so we've gone through a couple of steps in the lab. We specified the platform. The documentation talks a little bit about what each of these kernels is doing. In the AI engine, we have 3 kernels: the interpolator, the classifier, and the polar clip. The interpolator, again, is a 27-step half-band filter. Excuse me, just interpolation filter by 2. Then we have the memory map to stream and the stream to memory map, which those are kernels that are going to go into the programmable logic, and they're going to be created through the HLS flow. So for right now, that is a future activity, something we'll do later on in the exercise. The first thing I need to do is to verify that this component works. So I do that by building it for simulation. So if you look at the tool layout, in the upper left-hand corner are the various components that we're going to create. So right now I just have the one. If we come down to the flow window, you can see for each component, and right now again there's only one, there are various compilation steps or execution steps that can be run for that particular component. So right now I can build this either for x86 simulation or for AI engine simulation. The difference between the two being that x86 simulation is fast, but it's functional verification, where a C model gets created that actually runs on the host processor, wherever you have the Vitis tools installed. Meanwhile, the AIE simulator is using the actual simulation tool and compilation tool that's provided in Vitis, but it is a separate and unique compiler for AI engine modules or kernels. This tool actually comes from Synopsys, but it's integrated into the overall Vitis environment, so you don't see it as a separate tool. So I'm going to build this for x86 simulation, and then I'm going to run that simulation and compare it to the expected set of outputs. This simulation will be bit accurate, but not cycle accurate. For complete simulation, then I run the AI engine simulation. So again, just a quick sanity check. What have we done thus far? I'm going to eventually build an entire system, but right now I only have one component, and it's a AI engine component that contains 3 kernels. And the connectivity between those kernels, as well as the memory requirements, is all specified in the graph. So while this compiles, let's take a quick look at that graph code. So I'm just going to open this up, go to sources, go to AI engine, and look at the lower level graph. This specifies that there are 3 kernels, identifies each kernel by name, specifies the source, like what is the actual CC file that's being used for each one of these, specifies the connectivity, how one kernel connects to the next kernel, and how the first kernel and the third kernel also connect to the input and output of the graph itself, along with information that specifies how much memory. Because in the AI engine, every data movement is a memory read or write. So we need to specify how much memory is actually being utilized. So that's all contained in the graph code. So now this is finished. So the build for simulation is finished, and we can actually run the simulation. To run the simulation, I'm going to come back up, I'm going to collapse this, then expand out under settings, and under the launch.json, I already have one configuration for an x86 simulation and another configuration for an AI engine simulation. If I were going to create additional ones, then I could do that here, and then I could give it a different set of parameters. But I'm just going to use the one that's already here. So I'm going to just come back down into the flow menu, and I'm going to say run. So that runs really quickly. It's already done. And as a result of running that simulation, I now have an output, and under the x86 simulation output, there is a file called data, and it contains a file called output.txt. So where did output.txt actually come from? As part of the graph code, we go back for just a moment and look at that, we specified that this graph, which encapsulates the kernels, was going to be connected to the input file for stimulus and then connected to the output file to write the results of the simulation. And that's what you're seeing here on line 57, where for the graph itself, we specified that is a PLIO output. It's called data out 1, 32-bit, and it's going to write to a file called output.txt. So that file is being created and overwritten each time I run simulation with the results of the simulation. So what do those results actually look like? Well, if I double click the file, and I can now compare this to the golden.txt. So let me close these other windows so that I can now just have the golden.txt and the output.txt. And I want to now just create a new horizontal group so that I'm looking at both files at the same time. So I don't have a means of automatically comparing them, like doing a diff or something like that. So I have to do a visual inspection. And remember that the last stage of this logic assigns each output to a particular quadrant. And overwhelming majority of the time, it was quadrant 1. So the value really doesn't change. It does change around 900 or so, here around 993. So I can look at that in both files and verify that indeed the output matches the expected output by looking at the data around 993, which is different than everything just being a 1 to begin with. So we can see that at point 993, 2, the 994 is 1, the 995 is 3. So that verifies that from a functional standpoint, this module works as expected. So the next stage is to now compile it for AI engine simulation. So I can immediately go here and start that build process. So I'm going to collapse this, just make my screen a little less cluttered. In fact, I'm going to do that up here as well. And I'm going to say build for AI engine simulation. Now this will take a moment to compile, and may actually just shorten the video a little bit by pausing until this completes. It doesn't really behoove you to sit here just watching this stuff compile. You'll have plenty of time for that on your own. The next stage in the lab would be to run the simulation for the actual AI engine simulation, and once again compare the output to the expected set of outputs. Now, I know from having run the lab already that it's going to be the same. So in the interest of time, I'm not going to do that, but I do need to build this. And part of the reason that I need to build it is so that when we start creating the system level components, then this AI engine component needs to have been compiled. So in the lab, they're showing us some highlights of the graph code, which we just looked at. Again, showing the connection between the individual kernels, the overall connectivity, other factors like the runtime. So we've gone through quite a few steps in the lab, and we're going to actually pick up with the next phase, where we're going to add the PL kernels. So note the documentation tells us that up until this point, in the previous simulation, the input and output were text files because we were at an early stage of development. We didn't have the system yet, so we didn't actually have any physical logic to drive data into and out of the AI engines. But now, as we start to look toward a system level implementation, we need to define what those components are and how that data actually moves between the programmable logic and the AI engine. So that means defining the kernels that are in the programmable logic, and that is the memory map to stream and the stream to memory map components. So that build completed. Great news. We're not going to run the simulation, but we are going to start building the components for the programmable logic. So we're going to go back to the menu, and we're going to say File, New Component, and this time the component type is going to be HLS. And for the first one, we're going to be doing the memory map to stream. So just MM2S, again, write it to the same location, go to Next. Whenever we run HLS, there is a configuration file for every component. And that configuration file contains details about the expected clock rate, the clock uncertainty, the exact flow, and other information that's unique to this particular module. So what we're telling the tool is that we're starting off with an empty file, and we're just going to leave this at the default called HLS config. You could label it whatever you want. I'll go to Next, and now I'm going to bring in the particular source file. So I'm going to say Add File. Once again, go to this location, which for us is Home, Training. Go to the Lab folder. Under Support and under PL, I have both the code for the two different kernels that we're going to create here. And the first one is going to be this memory map to stream. So we say Open. So having done that, I now need to tell the tool what the top level is. So I'm going to browse, and now it's actually going to look at the file that I just identified. It's going to read all the functions in that file and determine what's the top level. Because again, this is a synthesis tool, so it needs to know where to start. I can have one file that contains multiple functions, so it needs to know what's the top level function. So that is correct, the memory map to stream. Click OK. I don't have a particular test bench folder that I'm using, so I'm not going to individually verify this at this time. I'll go to Next, specify once again what the platform is. So it's always going to be the VCK 190 for the purpose of this exercise. Click on Next. And then other configuration data includes what is the expected clock period. So remember, HLS is a synthesis tool. So you need to tell it exactly what the clock rate is that the module is going to run it. And in this case, we're saying it'll be an 8 nanosecond period. Excuse me. We can then also specify the amount of clock uncertainty. And the purpose of this is that of this 8 nanosecond window, which is what the tool is going to use for its own timing and evaluation purposes, we're saying I want to withhold 12% of that as just uncertainty, so that when the tool reports, it has to report on the 8 nanoseconds minus 12%. Now, what's the value of doing that? This helps to ensure that once you take the component generated at this stage into the larger design, you're less likely to have timing issues where you have one tool estimating that it's going to meet timing, and then you actually go to implement that kernel and find out that it doesn't. So this actually gives you built-in margin for the downstream tools. We are also going to specify what the flow target is, and there are two choices. This tool can still be used to create individual IP that can go into Vivado, drop into the IP catalog, and connect to other IP. Or, for the purpose of what we're doing, we're going to do the Vitis kernel flow target, which means that we're going to generate a .xl file. And the .xl is a Xilinx object file. Click on Next. That brings us to a summary screen, then click Finish. So now I have two components. I have my original AI engine component, and I have the first of my two modules that are going to go into the programmable logic. Now I'm going to walk through the exact same steps again and create the stream to memory map kernel. So I'll go File, New Component, HLS, call this stream to memory map, have it right to the same location, leave this at the default, an empty configuration file with the name HLS config, browse to the source folder for this, which is going to be under Home, Training, the lab directory, and the support folder under PS, then stream to memory map. So open. Again, let the tool identify the top level. Not bring it in a test bench at this point. Click on Next, select the platform. Click Next, give the same information we did before, which is an 8 nanosecond clock period, a 12 nanosecond, 12% uncertainty. The flow target will be the Vitis kernel flow. And this is, as you can see, it already says it's going to generate a Vitis.xo file, but I have found that the tool doesn't actually adhere to that. It still wants to generate a Vivado IP. So I'm kind of click off that. Now I'm just clicking back onto it. And this will hopefully avoid the tool a little glitch right now, at least in the 2025.1 version, which is what I'm using, where it wants to generate a Vivado IP component rather than the Vitis XL. And that's what's going to be needed later when I go to build a system project. So I go to Next, come to the summary screen, click Finish, and now I'm going to have a total of 3 components. The original AI engine component, the 2 kernels that are going into the programmable logic, memory map to stream, stream to memory map. And now I need to actually synthesize these. So let me start with the memory map to stream. So selecting it here also selects it in the flow window. and I'm going to run synthesis. Whenever you run HLS synthesis, the results take about 60 seconds or less. And part of what I'm going to do here is verify the information like the clock and uncertainty and the flow target. So all that is correct. And I'm also going to say package output. That's send. So say run. Now I can actually look at the synthesis result. It's going to take place in less than a minute. And one of the things that I'm looking to see is that it does not write out a Vivado component, even though I clearly have specified that it should be a Fidus.xo. But again, this is a quirk that I have found in this particular version of the tool. In fact, we can see it here, exporting RTL as Vivado IP. See it on line 104 right now. So that tells me that this glitch in the tool is still there. And I'm going to have to resolve that because when I get to the system level, I need this to be the Fidus XO file. So I'm going to come back to that. I know that's going to have to be addressed, but I'll come back to it. In the meantime, I'm going to select the stream to memory map. Same thing, I'm going to say run synthesis. It's going to give me the same set of options. I'm going to verify this and say run. And once again, you can see that it says exporting RTL as Vivado IP. Again, even though that was not the menu choice. So in terms of rectifying this, if I look right now at the particular module, let's say the stream to memory map, and if I go under settings, if I go to HLS configuration file, then here I can see all this information. So you see that the flow target here clearly says Fidus and not Vivado. So again, this is a problem with the tool right now, and we'll see. When I get to the top level, I'll actually show you what the implications of this are. So for right now, let's just assume that this is correct. So I know it will complain later, but let's just assume that we're okay for the moment. So I've created the two lower level components. So that brings us to step 5, where we now actually build the components, which is what we just did. So we actually go all the way up to step 6. So now we want to create and build the host application. So this is the code that's going to run on the processing subsystem. This is one more component that we need to create. So we're going to go to the back to the menu, and we're going to say File, New Component, and in this case it's going to be application code. And we're going to call this Versal CoSIM PS. We'll click on Next, specify the platform. Because we're now talking about code running on the processor, we identify which domain. And the definition of a domain is you have this heterogeneous compute environment. Well, a given domain is a given processor and the OS for that particular processor. And so the processor in this case is the Cortex A72. The OS is Linux. And this particular domain is labeled as XRT. So we're leaving that at the default. We click on Next. And because we're running XRT, we also need to specify the Linux system root. And then ultimately, we're going to specify the kernel and the root file system. But for now, just sysroot. So we're going to browse. And for my particular installation, and this will be different for you, for my particular installation, this is under other locations, under computer, under op, under the Versal Common. And what Versal Common is, this is the Linux image, sysroot, the file system, everything that you need to run all the Linux drivers without any customization. Because otherwise you could go into Pedal Linux and create your own more specific Linux distribution. If you're not changing any of that, then you can simply use this. So under the sysroots folder, I would select this folder, which is the Cortex 72 and 53. Select that, and then update the workplace preference, which means that having made this selection one time, I will not have to make it again because it now becomes a property of the workspace. So I can click on Next, and now bring in the specific source file that I intend to use. So I'm going to click on Add File, go to the location, which again is always under Home, Training, the specific lab folder, under Support, and now under the PS. So I'm going to start with this host.cpp, which is the top level code. And then I'm going to do the same thing and go back to that exact same location and get the data.h file. So again, Home, Training, System Flow, Support, PS, Data Flow. So you can see I have both files haven't been identified. Copy sources to project boxes check. Click on Next. That brings me to a summary screen. Then I click Finish. So I now have 4 components. The 2 PL-based components, the original AI engine component, and then now this processing subsystem application. So as part of the processing subsystem, we need to tell it which version of the CMake standard we're using. So we're going to expand this, go under Settings, then under User Config CMake. Just close some of these other windows. Under Miscellaneous, there's an option here to specify which C++ standard. And we're using version 17. So I make that determination, then I can close this, and now I'm ready to build this file, and I'm going to build it for a hardware deployment. So I will click on Build, making sure, of course, that I have the correct component specified, And for me, that is this Versal COSIM PS. So I'm going to build this, and this will actually be pretty quick. Okay, so that is done already. So these are my lower level components for this particular project. I have two kernels in the programmable logic. I have one in the AI engine that uses three different individual kernels. Then I have the application code. I'm now ready to start building the system project. So that brings me to step 7 in the exercise, where I'm going to create a new component. And this time the component is going to be a system project. And I'm going to call this Versal COSIM system. I will click on next, specify again the same platform. And now I need to give it the remaining information about the common Linux libraries, including the kernel and the root file system. So I will click on Browse, go to that same location. So for me, that's in my particular environment, this is other locations, computer, op, the Versal common, and there is the image. And then for the root file system, pretty much in the same location. Once again, update the workspace preference so that if I need to do other compilations, this information will already be defined for this particular workspace. So I can click on next, get to the summary screen, click finish. So you'll notice when this particular component gets created, which is my system project, it comes in as red because it's incomplete. In fact, it immediately shows me the system project settings, and I don't have any associated components. So I will come over and I'll start defining what are the low level components that make up this particular system. So I start by going to the hardware linker settings, and I need to create a new binary container. So for the information that's going into the programmable logic, this will be a binary file. So it's going to go into a binary container. So I will click on plus to create a new binary container. I'll just leave the default name binary underscore container underscore 1. And I indicate that both of these kernels are going to go into that particular container. So I'll click OK. So now that creates a binary container by this name that has those particular modules within it. But I need to add other components. So I'm now going to expand this. And where it says AI Engine Graphs, you can see that those two are already identified, the memory map to stream, the stream to memory map. But I now need to add in this graph, which represents the AI engine functionality. And there's only one graph in the entire design, and it is this Versal COSIM AIE. So I select this, click OK. And now, if we look at the window, we can see that this is now added. So I have the three components, and now I need something called a link configuration file. And you can think of this as like a netlist. where I need to explicitly tell the tool that the components in the programmable logic are connected to components in the AI engine. And this is how they connect. So I'm going to need to edit this file, the container1 link.config file. So I click on the file. This brings up the property window. I want to look at the source editor. And as part of this, there is a section here called connectivity. And I need to edit this. And I need to edit it by hand to create the specific connectivity. So the way to read this, this identifies, first of all, what kernels exist. So number of kernels for a memory map to stream, there is 1, and it has the name memory map to stream _1. Number of kernels for stream to memory map, there's 1, and it has the name stream to memory map.1. But we need to edit this code to reflect this syntax that's at step 7-2-11. So that begins with editing this so that the names are correct. And then adding the physical connection. So syntactically, we're saying we're going to have a stream connection because we move data from the programmable logic to the AI engine over a streaming interface. And this is a stream connection between the following two kernels. So memory map to stream .s. So it's the .s pin on that particular kernel. This is going to connect to AI engine _0. So that that's a specific instance of the AI engine in the netlist, and it's going to connect to this particular pin, which is called data in. And you may recall when we looked at the graph code, the data in was the name of the input to the graph itself. So that's where that name is derived from. Then on the other side, remember we're pushing data both into the AI engine and then from the AI engine to the programmable logic. So it's a streaming channel going in both directions. So this is going to be a streaming connection between the AI engine instance 0, the pin data out, one, being connected to the other kernel that's in the fabric, which is called stream to memory map, and the S pin on that. So again, this is something that has to be edited by hand, and you are literally connecting kernels and the AI engine to kernels and the programmable logic, specifying the connectivity between them. So I can, I don't need to save this, although I can. If everything that you do in this environment is automatically saved. So I'll just close this. And I could close the information on the binary container editor. And now I'm ready to package the project. So I come down under package config. And one thing that I need to tell it is to, under AI engine, to do not enable the cores. So by default, when the cores are loaded onto the device, they automatically enable and they just start running. Well, in this case, we don't want that to happen. We want the cores to run under the control of a test switch. So we're going to say, do not enable cores, and then we can verify that this command is in effect or this particular directive if we convert this to the source editor and we see that defer AI engine run is now set to true. So now we need to add the host application. So that's the one thing that's remaining from our system. Remember, all this at this level is about building the system level project. So we're going to go back to this tool, to the Vitis sys JSON file. We're going to come back up to components. And we come back up to where it says add existing component. I'm going to click on that. And the type of component we're now adding is going to be application. So it basically looks, says, well, great. How many application components do I have? I only have the one currently, so that is selected. I click OK. So now if you look at this component window, you can see everything is now part of the system level project. So now I've completely defined it, and now I'm ready to build the system project. So I can close this. I don't have to, but otherwise you just have so many windows open. And we're going to build this for hardware emulation. So we're going to click on Build All. And again, I fully expect that I'm going to get an error telling me that after I select tell it exactly which components need to be part of this. So this just basically says which components to build. I can select these, but if they've already been built, then the tool will recognize that. But it doesn't hurt to select them. And click OK. So then it starts to compile. Okay, so this is going very well. So I did do something a little bit different this time when I actually did the synthesis. I clicked on the additional option for generating the output synthesis product, although that wasn't explicitly in the lab documentation, and looks as though that may have alleviated the issue, because even though it wrote out the Vivado IP, it looks like it also created the .xl. Otherwise, I would expect this to, okay, well, it's actually rebuilding it. So it actually redid it again, and you can see now it's exporting that as IP, which no doubt means that when it gets to the top, it may have problems because it can't find the .xl. But we'll know. We'll know soon enough. So if this compilation is successful and if it completes, then we get to the last stage of the lab, which is actually run the system level hardware emulation. So to do that, by the way, we would select a particular component, then we would indicate that we want to create a new launch configuration, which is the way you set up the simulation along with whatever options you want to be in effect when you run simulation, like whether or not you want profiling, whether or not you wanted to generate a timeline. All right, I'm looking at the result of this, and I feel I'm letting myself be cautiously optimistic at this point that I will not get an error. So if that's the case, then if you're running this lab on your own, you're going to need to pay particular attention to when we did the synthesis options for the memory map to stream and the stream to memory map. I also clicked on the option to generate the synthesis output. Okay? And that's the only thing that's not in the lab documentation. And when that wasn't done before, again, it would only put out the Vivado IP. It was not creating the .xo file that's necessary at this stage. So it looks like it did that, and I'm basing my assumption here on the fact that this has gone through quite a few steps of compilation at this point, and it still hasn't complained about that. And when that's not there, it complains almost immediately. So that tells me that that is at least a necessary step, if not a workaround. I think they just need to update the lab documentation so that it's clear that you need to do that particular step. So what I'm going to do is, in the interest of time, I'm going to pause the video and I will restart when this successfully completes the overall compilation, because this still could take a while. I mean, even without errors, this compilation step might take a bit. Okay, so you can see, looking at the console window, we did build successfully. And to that end, I want to note something that's a little bit different than the lab instructions. So just in case you are doing this procedure on your own at some point, when we compile the kernels for the programmable logic under HLS, we clicked a specific option. So let's go back and actually show you that. So bring up this module for just a moment, go to synthesis. When we ran synthesis, we clicked on package output send. So that was necessary for the tool to create the .xo file above and beyond simply selecting Vitis as the flow target. So remember that, because it's not part of the documentation, but that was a necessary step. Otherwise, we get the error that it doesn't find the .xo file when it goes to build the system. All right, so now we're ready to run the system level simulation. So to that end, we are going to select the Versal CoSim system, going to expand, and under settings, we are going to click on the launch.json. And we're going to create a new launch configuration. So we simply clicked here, and we are selecting hardware emulation. This, by the way, is where you're going to spend the overwhelming majority of your time. You have options, of course, to download to an actual board, but in terms of visibility, being able to simulate your code, being able to walk through, being able to profile, being able to do extensive debugging, this is where you want to spend most of your time, and then generate a bit file or PDI when you're actually ready to go to hardware. So we've created a new simulation run, and now we can come back to the flow window and actually start the emulator. So when we do that for hardware emulation, we also have the option to now show the waveform. And show the waveform means that when the simulation starts, this is going to open up Vivado and allow us to view signals in the Vivado simulation environment. And that allows us to effectively tie together 3 different simulators: the AI Engine simulator, Quick emulator for code running on the processors, and then the Vivado simulator for kernels that are in the programmable logic. So we're going to show waveform. You also have the ability to enable trace functions, which will give you a different view. And this looks like a kind of a waveform, but not quite. You're actually seeing events. You're seeing a timeline of everything that happens and how it executes from beginning to end. So we're going to go ahead and say start. So since we enabled the waveform, this is going to start up the Vivado tools and open up the Vivado simulator. So that will be just a couple of minutes for that to initialize. When it starts up, we're going to change the signals that we're viewing. By default, the tool opens up with the signals that are in the top level test bench. So that's always true when you run the Vivado simulator or when you launch the Vivado simulator. You can then navigate to whatever specific signals or subsignals you want to view. So we want to view the AXI streaming signals that are moving data from the programmable logic into the AI engines. So we'll let this start up, we'll let the window initialize, then we'll change the actual signals that we're viewing. Okay. All right, so the simulator has been launched. We are going to select the signals that are shown by default. We're going to delete those, and then we're going to push into the design hierarchy, go down to this level, and we are looking for this set of signals. These are the AXI interface signals. We drag those to the waveform. We change the time of the simulation to 150 microseconds. We start this simulator, then we come back to the Vitis view, and we need to start or click on run for the hardware emulation. So what you're viewing now, and obviously we have to do a little bit of navigation to go back and forth between the two. We've got the emulation running in this window. So this is basically Quick Emulator. You've got the output tab here. This will be the actual test bench results. And then you've got the Vivado tools running in the background. So if I go here, we can actually see the respective waveforms. Let's try to move everything over so we can see as much of that as possible. So this will take a while because Linux needs to boot, and that will take anywhere from 8 to 10 minutes by itself. So let's go back to Vitis. Go back to the task, the emulation window. And at some point, this will successfully boot. And then once Linux boot, then we are going to type the command. So it's going to stop at that point, and it's now going to wait for our input. And at that point, we are going to issue the command to basically run the Vercel cosmps and incorporate the binary container _1.xcl_bin. So that's instruction 9-1-16, but we need to wait until Linux boots. Okay, again, this will take a couple of minutes, so we're going to pause the video until we get the prompt. When we get the prompt, then we'll enter the command to actually run the application. Okay, and we are there. So we now type the command. And specifically what we're doing is we're calling the application. So the application, if you recall, was the Versal COSIM_PS for running on the processing subsystem. And then we are specifying the binary container, which contains the information for the modules and the PL. And that file type is a XCL bin, which is a binary file. Right, so that kicks off the actual application. Now, if we come back to the Vivado waveform window, if we let this run for the full amount of time, then eventually we see data actually moving along that AXI interface from the programmable logic to the AI engines. So let's summarize what we've done in this particular lab, because we're now pretty much at the end. So we started off by building the individual components necessary for system level simulation. So for this particular lab, those components involve the AI engine, the processing subsystem, the programmable logic. And we needed to pull those together. So once we had created the lower level components and done individual verification, we then created a system project, and we tied those elements together along with a hand edited file called the system configuration, which showed specific connectivity between the kernels in the AI engine and the kernels in the PL. Once we built that, then we were able to run the hardware emulation. And once again, this is where you're going to spend the overwhelming majority of your time at this level, because once you've created your system, this is the facility that allows you to do observation, verification, single step through the code. You can run the debugger, and ultimately this is where you gain the most information before you actually generate a PDI and start programming the device. So again, this will eventually get to about 150 microseconds, and they tell us that that may not be long enough. Like, we may need to add another 50 microseconds to this. Well, we're going to end the video at this point.